variations in the values of G with R. Okay, what does this sentence mean? All right. So what is G again? We remember that G is gravitational acceleration. So meaning to say how fast you accelerate because of the gravity of any planet or body. And R being, if you remember, is the distance between the two bodies. So what we're studying right now is how does changing R change G? Or if we were to change the distance between the two bodies, how does it affect the gravitational acceleration? That's what we're talking about when we say variations in the values of G and R. So that's the question. How does changing one affect the other? You always have to ask that question in physics. Okay? There's an experiment actually for you in the textbook that we're not going to do right now. But basically, the relationship of G and R, it changes depending on how far it is from the Earth. Right? Now, value G is directly proportional. I'll repeat. Value G is directly proportional to the distance from the Earth, from the center of the Earth, if small r equals big R. I'll explain later. Value G is inversely proportional to the square of the distance from the center of the Earth for small r is equal or larger than big R. So if we were to look at a graph, it would look something like this. Okay, so let me explain what I'm talking about. So R, big letter R, what is big letter R? Big letter R is the radius of the Earth. Right, so if you don't remember that, write that down in your notes. Big letter R means the radius of the Earth, our planet Earth. Okay, small letter r is the distance between the two bodies. Excuse me, I'm going to repeat that one more time. Big letter R is the radius of the Earth, meaning to say from the center to the surface of the Earth. R is the distance between the center of the two bodies. So what this is saying, if the distance between the two bodies, small letter r, between the two bodies is smaller than the radius of the Earth, then the value of G is directly proportional. All right, meaning to say when R increases, G also increases. In other words, if you were standing on the surface of the Earth and there was a hole that goes all the way to the middle of the Earth and you fell down, right? The further you fall, the closer you get to the center of Earth, the slower you start to accelerate. The slower you accelerate. You're still accelerating, but the amount of acceleration actually starts to get slower and slower. Meaning to say, on the surface of the Earth, the acceleration is more, and at the center of the Earth, there's actually less acceleration. Now, at the same time, value of G is also inversely proportional to the square of the distance from the center of Earth if and when R is equal or greater than the distance of the Earth. Meaning to say, when you start to get off the Earth, the value of G actually also starts to get weaker. So it's actually kind of an interesting thing. It's kind of an interesting concept. But basically, if we were to take a look at the graph, it's like this. When small r equals capital letter R, meaning to say an object is on the surface of the planet Earth. That is the maximum. That is where the acceleration is highest, right? If you go closer to the center of the Earth, the acceleration starts to get less and less. The value of G starts to get less and less. And the closer you get to the surface of the Earth, the value of G also starts to increase proportionally, just like this graph. At the same time, the further away you get from the surface of the Earth, the value of G also starts to decrease. It also starts to get smaller. So when you're calculating, you have to check first whether the small letter r whether small letter r is smaller than big letter R, or if small letter r is bigger than big letter R, right? All right, let's continue. So here is an example question. Figure 3.12 shows a satellite with height from the surface of the Earth. R is the radius of the Earth, and R is capital letter R is the radius of the Earth, and small letter r is the distance of the Earth from the center of the Earth, which is the radius of the orbit. All right, now let's continue. So at height h, height from the surface of the Earth, distance from the center of the Earth is r equals big letter R plus h, right? That makes sense, right? To get the distance of the satellite from the center, you have to add the radius plus the distance from the surface. That just makes common sense. That's just basic mathematics. To get the value of small letter r. Okay? So if we were to put this in the formula that we learned earlier, which is small g equals large G plus r square, this is the formula that we would use. Right? Okay, remember that this is basically the formula that we use. Now, on the surface of the Earth, so if someone was standing on the Earth, then your height would be basically 0 because there's no height between you and the Earth. So therefore, r is equal to the radius of the Earth because r plus h is 0. So big R and small r is going to be the same. So gravitational acceleration on the Earth, you don't have to add the h. It's just g equals gravitational acceleration equals gravitational constant times mass of the Earth plus r squared, radius of the Earth squared. So these are two different formulas that we use. So when do we use these two different formulas? We use this formula when there is a height, when something is away from the surface of the Earth. So something like a satellite or another planet. For something on the surface of the Earth, we use this formula. All right? So just make sure you know which formula to use and when to use it. All right, next slide. All right, let's do a couple of example questions. All right, so here is an example question. Mass of the Earth, this is in your textbook so you can follow along. Mass of the Earth is 5.97 times 10 to the power of 24. So let's see what information we have. Mass. So mass is given as 5.97 times 10 to the power of 24. That's quite a big number. Please take out your calculators and calculate along with me, okay? Radius of the Earth. So radius of the Earth, remember, is capital letter R, is 6.37 times 10 power of 6 meters. This is kilos, this is meters. All right. Calculate the gravitational acceleration on the surface of the Earth. Now, it also gives us the gravitational constant, which is, gravitational constant is 6.67 times 10 power of negative 11 Newton meter kilogram. So this is the information that we already have right now. And now the question is calculate the gravitational acceleration. So gravitational acceleration is, if we remember, is G. So this is what we need to calculate. Okay, hopefully everyone so far is clear. All right, so take out your calculators. Let's calculate this. So what is the formula that we're going to use? Okay, since we are on the surface of the Earth, then this is the formula that, since we're on the surface of the Earth, like in the question, and this is the formula that we're going to use. So G equals capital letter G mass times R square. So going back to the question, let's write down the correct. So small letter G equals capital letter G M over r square. So this is the formula that we're going to use. All right. Now just put in all the correct values that we have. So G is what we're looking for. Capital letter G we know is 6.67 times 10 power of negative 11. Okay, mass we also know is 5.97 times 10 power of 24. And over radius, but you remember you have the square, so 6.37 times 10 6 square. Okay, and your final answer is what? What's your final answer? It's actually in your textbook, so can someone read the final answer? How many newtons? Okay, so if you have a mistake on your calculator, sometimes it's because of the way you wrote it down in your calculator. By the way, when you're using your calculators, you need to also learn how to write it down correctly. All right. Okay, what's the answer in the textbook? I don't have the textbook in front of me. Actually, even without the textbook, we know that the acceleration would be 9.81 meters per second. 9.81. So this is the gravitation. This is actually, and all of you should know this by now, gravity is 9.81. So we're just using the formula to prove what we already learned in the past. This is just for us to prove that the gravitational acceleration is 9.81. So on the surface of the Earth, gravitational acceleration is 9.81. Okay, so far so good. Can you still hear me? The rain has started to get louder here in my house. Hopefully you can still hear me. This is why I use a microphone, because if I were just use my cell phone, habislah, tidak dengar itu. Alright, let's go into the second example. So the second example now, this is an example of something that's away from the surface of the Earth. And dia jauh daripada bumi. So since it's far away from the Earth, then this is the formula that we're going to use this time. We're going to use this formula where something is further away from the Earth, which is small g equals capital G times mass over radius of Earth plus the height square. Okay, so let's look at the question. A radar imaging satellite orbits the Earth at around a height of 480 kilometers. So the distance, or rather height I should say, so h is 480 kilometers. We need to convert that to meters, so 400,000 meters. What is the value of the gravitational acceleration? So all the other information is given. So capital letter G is 6.67. And you should memorize the value of capital G, because it's going to be the same for the Earth. Okay, that's not going to change. Okay, M. So M is the mass, total mass. So 5.97 times 10 power of 24. Right, R is radius of the Earth, which is 6.37 times 10 to the power of 6. So once again, this time we're using this formula. So the formula that we're using this time is different. Remember what a distance from the surface of the Earth, so we're using this formula. So G equals capital letter G mass over R plus h square. Alright, let's continue. So we just put everything in the formula as usual. So let's go. G equals GM RH squared. So G also equals, let me use a different color. Let's use blue. So G equals, capital letter G is 6.67 times 10 power of negative 11. M is, again, 5.97 times 10 power of 24. Okay, I don't have enough space to write it out, but whatever. You know what I'm talking about. Okay, and then these two. So R 6 plus the height, which is 4,000. You can also write it out in standard form. You could also write it as, how would you write this as? 4.8 times 1, 2, 3, 4, 5 times 10 to the power of 5. You can also write it like that. Either way is fine. Alright. Meters. And remember, you have to square it. Alright, and what is our final answer? Someone read out the answer from the textbooks, please. Alright, so if you go by the textbook, it says 8.49. Now I want you to notice something. So meters per second. The acceleration, if you've noticed, is getting lower, right? It's getting lower, meaning to say the further we get away from Earth, the lower the value of G begins to get. Meaning to say, the further away we get from the surface of the Earth, the lower the gravitational acceleration, or G. So it's very interesting. Alright, so we can conclude that the further we get away from the surface of the Earth, the weaker or lower the gravitational acceleration. Okay, that is a concept that you need to remember. Alright, so good. So here's the question. Now why? What's the point? This is the question now. What's the point? What's the importance of knowing the value of gravitational acceleration? I'm going to read it. Gravitational force is a universal force. Therefore, the formula small letter g equals big letter G times mass times the square of the distance between the two bodies can be used to calculate gravitational acceleration on the surface of other planets, of other bodies such as planets, the moon, and the sun. So the question is, which planet has the largest gravitational acceleration? Which planet has the smallest gravitational acceleration? So why are these things so important? So these things are important. This is why it's so important. When the value of the gravitational force on the surface planet is known, the magnitude of the gravitational force on an object on the surface of the planet can be calculated. Knowledge is on the valued gravitational acceleration plays an important role in space exploration and continuity of life. This is why it's so important. Space exploration. Many scientists are interested to explore the other planets, not only to gain more knowledge, and not necessarily just planets, but like the moon and asteroids and other things. Not only to gain more knowledge, but also for money, right? Because, we might find that other planets have a lot of gold or silver or other types of metals or minerals that are very important, right? But the thing is, different planets will have different amounts of gravitational pull or gravitational acceleration. We know that the moon has less gravity than the Earth. Okay, what about other planets? Alright? If we go to another planet and we are not ready for the gravity, it could cause a lot of problems. For example, the planet Jupiter. The planet Jupiter has gravity that is many, many times stronger than Earth. So if you want to explore Jupiter, first of all, you need to make sure that your ship is strong enough to stand the gravity. You need to make sure that your rocket engines are powerful enough so that after you explore Jupiter, you can run away. Imagine you try to explore the planet Jupiter and you find out that afterwards that your engine is not strong enough to leave. You're basically stuck. Or, you have to make sure that the humans are strong enough. You know, are the people strong enough to survive in that kind of gravity, 10 times gravity? Or maybe it'll be like Dragon Ball. You know, you train in 10 times gravity and you become much stronger when you come back to Earth. I don't know. We've never had a chance to do that before. What I'm saying is, if you want to explore other planets, you have to understand, you have to know the gravitational acceleration of that planet. Is it worth knowing this type of stuff outside the field of space engineering? So it's not only just when you say space engineering, so it's not just we don't just use this in outer space. We also use it in our own technology here on Earth. So, for example, our space station, when we're using satellites, when we're launching satellites to create Wi-Fi, the wonderful Wi-Fi that's allowing us to have classes now. You need to understand the gravity of the Earth. We need to understand, okay, how much gravity, how fast will the gravity pull the satellite, so that we can adjust the satellite to have a perfect orbit. By the way, we'll talk about satellite orbit later today as we continue. Right? And but outside of these things, is it worth knowing these stuff? That's a good question. Basically, it's really only up to you. Is it worth knowing something? Is the knowledge by itself valuable enough? Some people say yes, and some people say no. You know, I've met people who think that any space exploration is useless, and some people think that all knowledge is useful. So my personal opinion is this: even if we don't necessarily go explore space, just the technology that it brings, you know, we need to have technology to understand the other planets and to learn about these things. Even if we never explore these other planets, the technology that we create while trying to study the other planets, we can bring this technology into other things in life. Right? For example, computers. One of the reasons why we started creating computers, because we needed machines that could make calculations to bring us to other planets or study other planets. Right? That was what we used computers for at first. And as the technology of computers begins to get stronger and stronger, the technology also becomes useful to other people. Just like what we're doing now, we have the computers and devices that help us to do work and to study. So in a way, yes, it is worth knowing this type of stuff outside of the field of space engineering. Okay, but maybe you don't necessarily need to know everything. And of course, nobody knows everything about space. Nobody does. But I believe that, at least I personally believe that, you know, just the act of looking for more knowledge is beneficial overall. But that's a good question. And I know not everyone agrees with me. Alright? Yeah. So, continuing. Like, we live on Earth where gravitational acceleration is 9.81. Yeah, we talked about this. Okay? Exploring space, you know, body of astronauts can be exposed to high or low gravity conditions. What are the effects of gravity on the growth of humans? I don't know how many of you have seen the movie Wall-E. I think Wall-E came out like 2000. Forgot when Wall-E came out. 2008, 2009. But if you've seen the movie Wall-E, it's about the story is about how humans have left the Earth and left behind robots on the planet to take care of the Earth. Now there's a scene in the movie Wall-E where they show that the bones of the people in the ship have become weak because they've been living in zero gravity. And when you live in zero gravity, it means that your bones never have to carry anything. And that is actually true. There's a lot of truth in that. If you're always exposed to zero gravity, your bones will get weaker. This is what happened to astronauts who spend a lot of time in space. When they come back, their bones are actually weaker. But at the same time, they become taller. So it's kind of interesting. Their bones get weaker, but they get stronger. I mean, not stronger, but they get taller. But yeah, so the effects of gravity does have an effect on the growth of humans. All right, so that's why it's important to know these things. All right, continuing. So now that we've understood gravity, the now that we know that gravity has an accelerational force, probably the most practical use for this knowledge for us, which I mentioned a while ago, is when we're talking about satellites. So when we're talking about satellites, because satellites, it's one of our most advanced types of technology. It's very useful in the field of communication. All our cell phone works, all our Wi-Fi works because we have satellites. Elon Musk is planning to put a whole lot of satellites to launch a lot more satellites so that he can have his own internet service. And we're gonna talk about something called centripetal force. Alright, so figure 3.13 shows 3 positions of a satellite which orbits around the Earth at a uniform speed. Observe the direction of the velocity of the satellite at each position. So, this picture is in your textbook. Alright? Now I want you to take a look at the picture. There are 2 forces working at the same time. We have the direction of the velocity. So we have the velocity which is actually going away from the Earth. And we have the force of the gravity which is pulling the satellite out towards the Earth. So here's the interesting thing. If we were to remove this planet, alright, then the satellite would actually just continue going on in a straight line, right? At the same time, with the planet there, because the planet that is there, it's slowly pulling the satellite towards the Earth. Now, however, because it's so far away, it pulls the satellite slowly. Now, what happens when we combine these 2 forces? We have 2 forces that's happening here. So one is a force that wants. So let's just say this. Okay, let's use this microphone as the Earth. So at one hand, there's the force of the satellite is going this way. It wants to go away from the Earth. But at the same time, there's a force that is bringing the satellite towards the Earth. So because of these 2 forces working together, what happens is the movement looks something like this. While it's trying to go away, it's also being pulled towards the Earth at the same time. And that's how you get an orbit. So what scientists have discovered is that if the satellite is going and moving at exactly the right speed, and at the right distance away from the Earth, you can have a satellite that keeps on moving forward, and it never actually really goes away. Because it keeps trying to go away. The satellite keeps on trying to go away, and the Earth tries to keep the satellite next to it. It's like a boyfriend and girlfriend who can never break up. They can't decide if they want to be together or apart, right? They're always gonna orbit around one another. And so the Earth is not letting go of the satellite. So the satellite wants to get away, and it still is moving away, but because the gravity of the Earth, it never really goes away. And the great thing about this is you don't even need to use a lot of gas, right? Once you have it moving at the right speed, in space there's not much friction. Once it's moving at the right speed, it can keep on going, and then every now and then you just need to boost a little bit with the engines, and you can pretty much maintain the current speed for a really, really long time. That's how all those satellites that we have work. Alright, let me go on to the next slide. Alright, so an object in circular motion, right? Circular motion meaning going around something. Oh, I forgot to change to the lecture, sorry. So an object in circular motion always experiences changes in the direction of its motion, even though its speed is fixed. That's the important thing. It always experiences change in the direction of the motion because of the gravity. The gravity is slowly changing the direction, even though the speed is fixed. In chapter 2, you learn that a force is required to change the direction of a motion of a body. In chapter 2, and actually in form 2, in the chapter about Daya, you learn that a force can change direction of a motion of body. The question is, what force acts on a body which is in a circular motion? We talk about that. It's the force of gravity that is acting on this circular spinning object. So for a body in circular motion, a force acts on the body in a direction towards the center of the circle. Meaning to say, for an object to turn around, to move in a circle, there has to be a force that is pulling it towards the center. Okay? In this case, it's gravity. So we call this force centripetal force. Right? Centripetal force. The opposite of centripetal force would be centrifugal force. Alright? Centripetal force. So here's an example. So we have you can see in this picture, we have an object that if you swing something around, you can turn something in a circle. So while the thing is actually trying to move in a straight line, because of the force that's pulling it towards the center, for example, a string, there's tension in the string that's pulling it towards the center, it will stay moving in a circle. Now, how big is that force that's moving it towards the center? Depends on the mass of the body, the linear speed, and the radius of the circle. So these are the three things that we need to know. So if we were to write it out as a formula, we would write this formula as this. So force equals mv squared over r, where F is the force, centripetal force, not petal, it should be T. M is the mass of the object, V is the linear speed, and R is the radius of the circle. So F equals mv squared over r. So if you were to try and solve a question, here's an example. Figure 3.7 shows a hammer throw athlete swinging an iron ball in a horizontal circle before releasing it. What is the centripetal force that acts on the iron ball when the iron ball is moving at a speed of 20 meters per second? So let's use the formula that we have learned. Alright, so the formula is F equals mv squared over r. Alright, let's look at the question. Alright, so what is the mass? So mass of the ball, of the iron ball, is 7.2 kilograms. Okay, I hope you're following along. And the ball, the speed of the ball is 20 meters per second. Alright, so we need to calculate the distance or the length of the string. The distance of the ball from the center is shown in let me show the picture again. So you can see the string is 1.7 meters. So R equals 1.8 meters. So now we have all the information we need. We have the formula. So it's just a matter of putting the correct values in the formula. So F, and follow along with me with your calculator. So 7.2 times 20, and remember this is a square, so you square this one first, then you times it with this one, and then R, which is 1.8 meters. So this is the question that we have. And what is your final answer? So if we were to find our final answer, so 20 times 20 equals 400. 400 times 7 times 2 equals what? 7.2 times 400 equals 2008. Right, so divided by 1.8. Okay, so you get an answer of 1,600 newtons. Yes, so meaning to say that string that you swing the ball with is pulling back at the ball at 1,600 newtons. Okay, now let's try something. Okay, let's try something. This is not part of the question, but let's try something. Let's see what happens if we were to spin the ball faster. If we were to spin the ball faster, instead of 20 meters per second, we change it to 40 meters per second. What will happen to our answer? So instead of 40, we get... Sorry. Yes, it'll increase, but to how much? It will increase, that's right. I'm asking you how much. How much will it increase? Calculators, guys. Come on. So 40. So 40 times 40 equals... So 40 times 40 equals 16,000. So 7.2 times 16,000 divided by 1.8. You would get 46,000 newtons. That's correct. So if we were to increase the velocity, then the centripetal force will also increase. Okay. What about if we were to increase? Okay, I think this is important. We need to figure out. All right. What about if we were to increase the radius? Let's say instead of 1.8, we'll have 3.6. 3.6 meters. So how would that change our final answer? 3.6. So instead of 1.8, 3.6. What would happen to our final calculation? Let's see. You would end up with... What's our final answer? 800 newtons. That's correct. That's correct. 800 newtons. Very good. All right. Now the reason why I'm doing this is I just want to show you how changing the different values will also how the value will affect the amount of force. So you can tell if the longer the distance, it actually starts to have less centripetal force. There's actually less centripetal force, even though we're moving at the same speed. And so this is how this is how scientists try to calculate. If we're going to launch a satellite, taking into account these three factors: the mass, the velocity, and the distance from the Earth, they'll calculate. Okay, what's the best distance for us to launch the satellite, and what is the best speed that we should launch the satellite so that we can maintain a perfectly balance. So this is the same mathematics that they use. Okay, let's go back. Let's try another example question. Do we have another example question? No, we don't. Okay, never mind. Now this is what's amazing. Okay, here's the question: can a satellite orbit the Earth without being driven by a rocket engine? I already told you, yes, you can. But the amazing thing is the possibility of such a movement was predicted by Isaac Newton in the 17th century. In the 17th century meaning to say 1600s. Way before a computer, way before any satellites, way before any of that technology was available, Isaac Newton predicted that this is possible just by using mathematics. This is why I was saying, even if we do not immediately see the views of the things that we study, that the knowledge that you gain will eventually, grow. When Isaac Newton was alive, they did not have the technology to test this prediction, even though he had the maths to prove it. But now it's a reality with so many man-made satellites orbiting around the Earth without being driven by any thrust. Meaning to say, once the satellite is in space, you don't need to use the engine anymore. Just turn it off and let gravity do its work for you. Okay? Where we use the gravitational force as the centripetal force. So instead of using a string, we just use gravity to keep the satellite towards the Earth. Right, so this is the picture in your textbook. So if you launch it at just the right speed and at just the right height and at just the right angle, then you will find that it will circle. Of course, you really have to calculate it properly. If you shoot it too high or at a too high of an angle, then you'll just end up throwing the rocket away. The rocket will fly away, never to come back. And you wasted millions of dollars. Okay? If you launch it too low or at a too low of an angle, then the gravity will pull it back to Earth. But if you throw it at just the right direction, at just the right speed, you'll get a satellite where it'll keep on turning around and turning around and turning around. And that's just amazing without any need for a rocket or something like that. This is why we study gravity. It helps us. Okay? I love this picture. This is the original sketch done by Isaac Newton. So imagine, Isaac Newton was able to figure this out and come up with this theory way before the computers and the technology was there for us to test it out. And even for us now, there are so many things that we try to calculate about space or about technology, and yet the equipment that we have is not yet ready, right? But that doesn't mean we shouldn't try to continue studying and pursuing the knowledge. All right. Centripetal, that's T, not D. That's a typo. By comparing the formula for force equals mass times acceleration and formula for centripetal force, force equals mass times velocity square over r, we obtain the formula for centripetal acceleration. Okay, so how fast is the acceleration of the centripetal force? Okay, where v is the linear speed of sound, r is the radius of the orbit. How do we get this formula? Simply by using substitution. So let me just go back to the whiteboard. We are using basically simple substitution. So if F equals mass times acceleration, and we also know that F equals mv square over r, then using substitution, we can say that mass equals mass v square over r square, and at the same time, because we can there's an m on both sides, we can simplify, so we can just cancel it out. So we end up with a equals v square over r. That's how we get the formula for centripetal acceleration. Alright, so we're probably going to do a couple of examples here. Alright, just a couple of examples. And then after that, we're done for topic 3.1. That's just topic 3.1, which is quite a long one. Alright, so figure 3.19, and again, this is in your textbook, but please follow along. Shows a weather satellite orbiting the Earth at a height of 480 kilometers. The linear speed of the satellite, meaning the speed in a straight line, is 7.62 times 10 by the power of 3 meters per second. This radius of the Earth, r, equals r 6.37 times 10 power of 6 meters. By the way, you should also memorize the radius of the Earth. Okay, because, the radius of the Earth doesn't change. So try to memorize that, 6.37 times 10 by the power of 6. The question is, what is the centripetal acceleration of the satellite? So the acceleration towards the Earth. And so centripetal acceleration of the satellite. So we could use the whiteboard and figure this out. Let's see what information we already have. Alright, so we have the height, which is basically 48 kilometers, 480 kilometers, or 400,000 meters, or 1, 2, 3, 4, 5, or 4.8 times 10 by the power of 5 meters. Whichever way you want to write it out. Since the other numbers are using standard forms, I'll use standard form as well. Okay, linear speed, or v, is 7.62 times 10 power of 3. Radius of the Earth, big letter R, is 6.37 times 10 power of 6. So what is the centripetal acceleration? So centripetal acceleration, meaning the formula we're using is A equals, let me just show you guys again. So A equals V square plus R. R being the distance of the object from the center. Now, if we have to be careful with this question, yeah. So common mistake is to just take r, radius of the Earth, and use that as our small letter r. But remember, small letter r equals capital letter R plus h. Okay, remember that because we are away from the center of the Earth, right? It's away from, it's not on the surface of the Earth. So we need to calculate, what we're calculating is the distance of the object from the center. That's what we need to calculate. So keep that in mind and do not forget that. Once you know that, then it's just a matter of, once again, putting everything in the formula. So A equals, let me use a different color for this solution. A equals V squared, so 7.62 times 10 to the power of 3 square over, you need to combine both of this, so 6.37 times 10 power of 6 plus 4.8 times 10 power of 5. Final answer is, what's our final answer? And our answer should be in meters per second. Someone? Textbook? What does it say? I don't have the paper textbook in front of me. Someone with a calculator? Okay, so 8 point. Thank you for telling 8.48 meters per second. So that is the centripetal acceleration, right? So what if we were to change it? Let's try change one of the values. Let's say, let's change the value. Let's change the distance from the Earth. Let's say the distance of the Earth is instead of 4.8, let's say it's 9.6. Then how would that change our answer now? So 9.6 10 by the power of 5. So how would that change our answer? Would it increase it or decrease it? Could you please calculate that? Prediction is to increase. Yes, your prediction is correct, but by how much? How much exactly? Yes, so now we're all learning to become Isaac Newton and predict things about space. So I'm also going to calculate 7.62 times 10 power of 3 okay, square. So if it's a square, then it's basically divided by 6 times 37 times 10 power of 6. Is it 9.9? Is it 9.1? Can anyone else confirm or deny that? I'm also still typing it on my calculator as well. Yeah, sometimes it's not really that fun to type things out on standard form. All right, so let's see what everyone's answers are. So a couple of people have gotten 9.1, which seems to match which matches the prediction of that it will increase. So basically, if we were to increase, if we were to increase the distance from the Earth, you actually need a stronger centripetal force acceleration to keep it, to keep it, centered around the center. Now, for satellites, we usually, because we cannot really change how strong the gravity is, so we have to base our calculations um, based on the gravity and the speed that we can launch a rocket. That's basically how we choose where to place our satellites. Okay, so let's continue. All right, so formula for the mass of the Earth. So last two slides. This one you can just see. This one you can just see in your textbook. The formula for the mass of the Earth and the mass of the Sun can be derived by using the formula for Newton's universal law of gravitation and the formula for centripetal force. So these two, by using these two by using these two formulas, scientists have been able to calculate the mass of the Earth and the mass of the Sun. And you can see in the textbooks how they do it. And it's really interesting how by using 2 or 3 formulas, they can calculate so many complex things, right? Okay, so we are basically done with 3.1. So your assignment for today is to do formative practice 3.1, page 95.